To welcome you. This is the lecture that you should have watched by the time that we reach MLK Day. This is the lecture that would have occurred on Monday, January 18th. We're starting Chapter 12. Chapter 12, we cover two of the most important techniques, or two of some of the more important types of analytical techniques that allows us to get structural information down about organic compounds. These are mass spectrometry and infrared spectroscopy. Structural determination of organic compounds has been difficult since man even started looking at these things. Also been a very time-consuming process. However, very extraordinary advances have been made that makes this such a much easier process. Two of the current methods that are used and that we're going to talk about are mass spec and infrared. Mass spectroscopy of small molecules can be analyzed by what are called magnetic sector instruments. You have a sample inlet. Somehow the sample is injected into a system, usually via a syringe through some sort of rubberized dividing material called a septa. It is introduced into a chamber where you have some sort of ionization. For the magnetic sector, basically it is a beam of high energy electrons. Many times they are generated by a heated filament. It's heated up so strongly that electrons are kicked out of the middle. These electrons plow into the molecules that were introduced via the sample inlet. The molecules fall apart because they've been plowed into by something that has so much energy that it breaks bonds. The different fragments are then drawn down this tube. They are selected and passed through what we call a slit. Since these fragments have different masses and charges, they have different susceptibilities to magnetic fields. Therefore, there are some fragments that, due to their mass and their charge, can be deflected more than others. Or you have those that are not deflected very much, or those, which is the green, or those that are deflected in the other sense due to the interaction with the magnet. These fragments strike some sort of detector, and we can get a display of the various ions and their charges in an intensity-based ratio. And I'll show you what that looks like in just a second. So this is what is known as a magnetic sector mass spectrometer. In the ionization chamber, let's look back here. Okay, we're introducing the sample into this ionization chamber. Again, you've got some source of electrons that are being projected through this sample, and they're plowing into all the various molecules of your sample. They're plowing into it with enough energy to cause bond fragmentation. So the molecule falls apart. It's based upon the mass and the charge that they have that they're selected out and detected. Basically, in the ionization chamber, small amounts of the sample undergoes vaporization, and then they are ionized because they've been plowed into with an electron, and here we have that, to form what are known as a radical cation. It has lost an electron. So this RH, whatever this organic compound is, it has been plowed into by these high energy electrons, and it's kicked out an electron, forming radical cations. These have charge to it. Because these have charge, remember, moving particles, flow of electrons creates an electric field, and wherever we have an electric field, we have a magnetic field. So these things, based on the mass, have a charge to them. So we have an amount of energy that's transferred by the ionizing electrons that cause the fragmentation of the parent organic molecule into the radical cations. It's transferred, depending upon how the molecule fall apart, it can be transferred into a radical cation, radicals, or neutral species, just depending upon how the molecule falls apart. The fragments then pass through a strong magnetic field in a curved pipe that segregates them according to their mass to charge ratio. So here they've been ionized, they've fallen apart, formed the radicals, the cations, and the neutral compounds. Just the radical cations make it through the slit. Since they have a magnetic nature to them that is based on their mass to charge ratio, their path is changed by their interaction with this external magnetic field. They're deflected based on their mass to charge ratio into those that are extraordinarily impacted by magnetic field, the external magnetic field, those that are not at all, or those that are somewhat repelled by the magnetic field. Positive fragments are sorted into a detector and recorded as peaks plotted along an axis that is based on a mass to charge ratio. So we can see on this chart, on this plot, what the mass of the ion is in that particular mass to charge ratio peak. Here we have a plot of a mass spec. The y-axis is how many ions of that kind are we seeing. Oops, let's do that. That may be a little bit better. Right here, the mass to charge ratio. This shows of the ions that we have, what percentage of them are we seeing? In this particular mass spec, we're seeing a bunch of ions that has a mass to charge ratio of 29. We've got others that come in at 28, 27. Here we're seeing other peaks at a mass to charge ratio of 44. So the plot of the mass to charge ions on the x-axis versus the intensity of the signal shows us relatively how many of the ions we're getting. The tallest peak in your mass spectra usually is set or normalized to 100%. That tallest peak, wherever it occurs, is called the base peak. So in this particular mass spectra, whatever the compound is, the base peak is at 29, because that is the most intense peak in your spectra. The mass to charge ratio of that ion fragment that represents the unbroken apart parent compound, the thing that just lost the hydrogen. Go back. The peak that represents this guy, the thing that only lost the initial hydrogen. This is called your parent peak. It corresponds to your parent peak plus, parent peak plus. So the peak that corresponds to the unfragmented radical cation is the parent peak, or the molecular ion peak. In this compound, it is probably somewhere above here. Okay, this mass spectra here parent peak is 29. This is propane. Where are my markers? Right where I put them. So C3H8. So C3, 36, 3 times the weight of one carbon. One carbon is 12. There's 3 of them. That's 36 plus 8 is 44. So this is the mass spectra of propane. 29 corresponds to a breaking of the bond in a radical process, or in a radical cationic kind of process, leaving a radical cation. The mass peak, M over Z of 44, represents the parent molecular ion. So this represents the weight of this entire thing, just minus an electron. That's your radical cation that you initially start out with. The 29 is something that this thing busts up into. Usually it is the ethyl radical. And you have this methyl radical that's lost. So M over Z of 29, carbon is 12, 24, 25, 26, 27, 28, 29. That is this radical fragment here. The difference between 14 and 29, 44 and 29, is 15. The weight of one carbon and 3 hydrogen is 15. So the 44 is this. The 29 is after this has fallen apart to give you that. So by the mass of the peaks and their intensity, we can get some idea of what the individual compound has in it and how it fragments and what the original parent molecular weight was. What kind of information can we get from mass spec? Well, the mass spectrum can provide the molecular weight of a compound. How heavy was it? In the previous spectra, we saw the mass spectra of propane. It told us that the parent molecular weight was 44. It also told us that the thing fell apart and gave a particularly strong ion at 29. The ion at 29 is almost exclusively a C2H5 radical. So it provides us the compound, the idea of the parent weight of the compound, but it also, if we understand how compounds fragment, it can tell us what the compound is because we know how molecules fragment. We can work backwards, piece all those things together, and give us an identity of what the compound is. So the way a molecule breaks down, can produce characteristic fragments that help in identification. The bad analogy that I give of this is if you have nieces or nephews, especially with nephews. I don't know why this is. You give a 5-6-year-old male child a block, a bunch of blocks, and he builds them up in a tower. What's the first thing that child is more than likely going to do? He's going to pretend like he's Godzilla and whoosh, blow through that tower. The tower is going to break apart into collections of blocks. Turns out when molecules undergo this fragmentation by being blasted with electrons, they fragment in characteristic, repeatable ways, such that a sample of sugar produced in China, when submitted to mass spec in China, will fragment the exact same way that a sample produced in Oklahoma, that a sample produced down in Venezuela, that a sample produced in Iceland, from a sample produced down in Africa, all those molecules of sugar will fragment in the exact same way. And they fragment differently from other compounds that are isomers of sugar, such that the pattern that they establish is fingerprint for that molecule. We use this routinely required as a forensic chemist. The mass spectra and the fragmentation pattern, we needed to know exactly how that molecule fragmented and why it did, in case we were asked on the stand to help the witnesses, the jury, understand how we came to our conclusions. So we had to understand this stuff. So we can also look and see if our molecule is big enough. We don't necessarily see the original molecule, but we can see how that fragments and also see how those fragments fall apart. So it allows us to get information about the structural identity of the molecule. For example, there is a specific kind of mass spec that's called exact high resolution mass spectroscopy. It can give the weight of a compound to 7 or 8 or 9 decimal places to the right of the decimal. Extraordinarily accurate. As part of my PhD synthesis, I had to provide this high-res mass spec analysis of every compound that I made to confirm its identity. So, we have a male sex hormone, testosterone. It contains, and this is an application I'm showing you, how we can use mass spec to identify the structure of a compound. We have the male sex hormone, testosterone. Let's say we don't know its structure, but let's say we've got mass spec information about it. We know, because it's a steroid, we know that it only contains carbon and hydrogen and oxygen. It has an exact mass of 288.2089 as determined by high-resolution mass spectrometry. What might be a possible molecular formula for testosterone? Well, we know that since it is an organic compound, 51% of the atoms present in the compound are going to be carbon. So if we determine the maximum number of carbons that could be present in our compound, that gives us a stepping off point. So if we determine the maximum number of compounds, let's say the organic compound is totally carbon. It's not, but let's start there. The weight for the compound is 288. If we divide that by 12, the mass for one carbon, 288 divided by 12 equals 24. That means if it was totally carbon and nothing else, no oxygen, no hydrogen, we can have a maximum of 24 carbons. But we know that this is a steroid. We know there are other elements present than just carbon. So there can't be 24 carbons because there have to be other elements present to come up to the weight of 288. So we can't have 24. Okay, let's back off on that. Let's not have 24 carbons. Let's say, I don't know, let's say we've got maybe from 16 to 20 carbons to leave room for oxygen and hydrogen to contribute to the mass of 288. So let's assume that there are somewhere between 15 and 20 carbons. So we assume 15 to 20 carbons. Okay, that gives space for the hydrogens to contribute to the mass and any oxygens that are present to contribute to the mass. Oxygen as an element is represented by three different isotopes: oxygen 16, oxygen 17, and oxygen 18. The exact mass is 15.999, 16.999, 17.999. Well, we can see that these numbers are really, really, really close to the whole numbers of 16, 17, and 18. So we're not going to have a large number of oxygens that can contribute to the 0.2089. These isotopes are going to be primarily affecting the 288. Because these are so close to whole numbers, we're not going to have 30 of these things. We're going to have maybe at the most 3 or 4. So 3 or 4 of these, this is such a close thing to a whole number that these isotope masses are not going to contribute much to the 0.2089 mass portion of this compound. Well, what's the only other element present? Hydrogen. So we can assume that the other hydrogens present contributes or is the only significant contribution to the 0.2089 part of the mass of the formula. If we subtract the primary isotope of hydrogen is isotope mass of 1. We have 1 minus, let me see, 1.00783. This is the exact mass to 6 sig figs of hydrogen. Primary isotope of hydrogen has an exact mass of 1. So if we subtract out that 1, mass weight of 1, we get 0.783. This is that contribution that the number of hydrogen makes to the decimal portion of the 0.2089. Therefore, if this represents the hydrogen contribution that results up to the 0.2089, if we divide 0.2089 by 0.0783, we should get the number of hydrogens that combine together to give us the 0.2089. So by doing that, just like we did with the carbon, we took the 288 and divided by 12. We're dividing this 0.2089 by the 0.00783. That gives us basically about 26 hydrogens. However, since we can't have fractional numbers of hydrogens, we can't have any more maximum of 27 hydrogens. So we have somewhere between C15 and C20, I don't know, maybe 27 to 30 hydrogens, plus a certain number of oxygens. That when we have the exact number of carbons, when we have the exact number of hydrogens and the exact number of oxygens, it will total up to be 288.2089. So there are tables that will have access to that have molecular formulas that contain carbon, hydrogen, and oxygen that contain somewhere between 15 and 20 carbons, somewhere between 20 30 hydrogens, and the number of oxygens who total up to be 288. So here we have a table of formulas that have somewhere between 15 and 20 carbons, somewhere between 20 and 30 hydrogens, and oxygens that come up to a total mass that is very, very close to 288. Well, that's just a little bit above 288. So we have C20H32O has a high-res mass of 288.2453. We have C19H28O2 that comes up to 288.2089, and we have C18H24O3 that comes up to 288.1726. So we can see that based on our high-res mass spec, that potentially the formula for C19H28O2 has the right number of carbons, hydrogens, and oxygens to get us to the right number for the molecular mass of our compound. So the possible formula for testosterone is C19H28O2. So this is how we can come up with a reasonable formula for a compound based on the high resolution mass spec of the material. This way of calculating mass is used pretty routinely in the way that I will show you how to look at and analyze mass spectra. More information besides the mass spectra than just its masses is present. Different kinds of functional groups, heteroatoms, things other than carbon and hydrogen, fall apart in particular patterns. And if you know what those patterns are, you can see those embedded in the mass spectra fragmentation patterns and say, oh, I see this kind of fragmentation pattern. This tells me that there probably is this kind of functional group in the mass spec. In the simplest of organic compounds, we have your hydrocarbons. Hexane. This is the mass spectra for hexane. Parent compound is at 86. That's the mass of 6 carbons, 14 hydrogens. Let me see, 3, 5, let's see, 2, 4, 6, 8, 11, 14, so C6H14. Molecular weight of 86. So that's what we see right there. That's the parent molecular compound right there at 86. It gets struck, it kicks out an electron, and it gives us the molecular ion at 86 right there. What this does, this molecule breaks down further. So we see this peak corresponding to the loss of an electron, but then now this is reactive and fragments, falls apart, and we can see how each of these molecules fall apart, or what happens to this molecule that presents different peaks in the spectrum. So if this hydrocarbon loses a CH3 group, this is 70, that's roughly 71. We can see a peak at 71. 86 minus 71 corresponds to a difference of 15. So if this radical cation loses a methyl group and forms this guy, the difference between this and this is 15. The parent peak at 86 could fall apart in this way. Lose an ethyl group, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. This thing kicks out and breaks the carbon-carbon bond right there. Gets gets us down to 57. 57 is the most intense peak. This is the base peak. The difference between 86 and 57, 86, 57, 29. The score 15 is a CH3, 29 is a CH3, CH2. Or this could fragment equally, break right in the middle, and give you this three carbon fragment with a weight of 43. Or it could break and give you this charged species, CH3CH2, the mass of 29. So when we see, usually in these long chain hydrocarbons, usually we can see logical losses of 15, where one carbon breaks, then the next carbon breaks, then the next carbon breaks, so we can see the loss of 15 between the peaks. So if we know how these molecules fragment, we can see, oh, it's got this kind of pattern. Generally, that indicates it's a hydrocarbon. (71 minus, let me see, if this 71 loses a CH3 group, 71 minus 15 is 56. Do we see a peak at 56? Yes. Okay, so this peak is the loss of a methyl group from this fragment at 71. See, 57 minus 15. 42. Do we see something at 42? Yes, we see something right there at 42. So we can see fragments of minus 15 even amongst the ions that are created from your parent compound. So this difference of 15 pattern in amongst all these peaks is something that is unique to long chain hydrocarbons. Can we see the difference between 43 and 29? 43 and 29. You see 9 and 4 is three. 43 minus 19. 43 minus 15. I'm sorry. 43 minus 15. Excuse me. 20. 28. Do we see 28? See a little bit of 28 there. So we can see these losses of 15 in amongst all the peaks. So if you can find those things, that can give you a hint as to what kind of functional groups you have in your molecule. Some of these losses are more common than others, but you can see this loss of 15 in straight chain hydrocarbons. The first kind of functional group that we're going to be looking at are alcohols. Alcohols can fragment in one of two ways. The first is what we call alpha cleavage. We break the carbon-carbon bond that is alpha to the OH. This carbon has the oxygen attached to it. Therefore, the carbon that it's attached to is the alpha carbon. This bond breaks, so this is called alpha cleavage. It gives you this radical and those resonance stabilized cations. So we can see a loss of, let me see, this is carbon, depending on what it's bonded to. Let me see. So we can have losses of this ion, which is resonance stabilized. Another kind of fragmentation pattern that we see in alcohols is called dehydration. We lose water. Water here weighs 18. We lose water from here. We get the radical cation remaining over. So if we find a difference of 18, that's very significant for the presence of an OH group. So if you have a parent molecular ion, and then you see something that is 18 units smaller than that parent molecular ion, that strongly suggests that you have an alcohol as your parent compound. Second kind of functional group are amines. When you have nitrogen in a compound, it's indicated by an odd numbered molecular weight. Let me show you why this is true. Ammonia. Nitrogen weighs 14. Hydrogen weighs 1. 14 plus 3 times 1, 14 plus 3 is equal to 17. Let's look at that next compound where we've replaced one hydrogen with a CH3. Nitrogen, H, H, CH3. All I've done to go from here to here is replace one hydrogen with a CH3. Well, this nitrogen is 14. Two hydrogens, 2. These 3 hydrogens plus 3 plus carbon is 12. 16 plus 15 is 31. So the molecular mass of this amine is the odd number 31. Let's replace another hydrogen with another CH3 group. So we have one hydrogen left, we have one CH3 and a CH3. So we have NH, 2 carbons, 6 hydrogens. C2H6, 2 carbons is 24, plus 6 is 30, plus 1 plus 14. 14 for the nitrogen, 1 for this hydrogen, 30, 24 from the 2 carbons, 6 from the hydrogens, 24 plus 6 is 30. 14 plus 30 is 34 plus 1, 44 plus 1 is 45. So this compound has a mass of 45. If we put on another carbon-containing group, the situation doesn't change. So if we have an odd molar mass to our compounds, generally that's a very strong indicator that we have nitrogen present. The compounds that you're going to be asked to work with will primarily only have one nitrogen in it. So the compound's molecular masses will generally be odd. How can or what kinds of fragmentation patterns do amines undergo? Primarily, they undergo what's known as alpha cleavage. Again, here's the carbon bonded to the nitrogen. The carbon that is alpha, right next to the carbon that is a nitrogen, that's attached to the nitrogen, that carbon-carbon bond breaks. This is the alpha carbon, therefore this bond breaks, therefore it's known as alpha cleavage. So they can generate alpha radicals, alpha cleavage to give this radical, and this stabilized, resonance stabilized nitrogen-containing cation. So the primary thing you need to look for with amines is odd molecular weights for their parent molecular ions. Another type of organic compounds are halides, alkyl halides. These have distinctive fragmentation patterns, such that when you see them, you can say, oh, there's a halogen present. With halogens, there are very specific isotopic weights and percentages that can distinctly identify what kind of halogen you have. If we have chlorine, chlorine exists in two isotopic forms. Chlorine 37 and chlorine 35. Sorry, chlorine 37, chlorine 35. Chlorine 35 is present in roughly 75%. So 75% of all the chlorines that we found are chlorine 35. The other remaining approximately 25% are chlorine 37. So here we have ethyl chloride. The parent molecular weight is 64. 2 carbons, 5 hydrogens, and a chlorine. So C2H5Cl. Carbon is 12, 24 plus 5 plus, let's say 35, or 34.5. 24 and 5 is 29. 29 and 34.5, 0.5, 9 and 4 is 13. 63.5 rounding up comes to 64. But notice, you have two relatively high peaks in the parent molecular weight area. We have one that corresponds to 54. But notice, this is awfully close to the chlorine 35 mass isotope. Notice its height. If we were to compare the height of this peak to the height of the M plus 2, well, there's a chlorine 37 that is 2 mass units higher than the chlorine 35. So one of these peaks, peak at 64, corresponds to that compound that has the chlorine 35 isotope. The other peak corresponds to the chlorine 37 isotope. So basically this ratio of these two peaks, the parent molecular ion and the M parent molecular ion plus 2, due to the difference in the masses of chlorine, in a ratio of 3 to 1, screams out there's a chlorine present. So this unequal peaks in the parent molecular ion area, M and M plus 2 in a 3 to 1 ratio, screams, tells you, hits you in the face with the pie saying there's a chlorine present. So here we have some other isotopic distribution of the various isotopes of some of the common elements. Hydrogen. Primarily, we have protium, one proton in the nucleus. It's not really 100%, it's 99.8% or something like that. The other smaller percentages are due to deuterium and tritium. We have carbon 12, carbon 13. Most of the carbon that we see in compounds is carbon 12. Nitrogen has two isotopes, N14 and N15. Nitrogen of the N14 species is 99.6% of the isotope. Oxygen, most of it is oxygen 16, 99.8. Sulfur, two isotopes, sulfur 32 and sulfur 33. Excuse me, sulfur 34. The lion's share of the sulfur exists as sulfur 32, 95%. But there's also sulfur 33 and sulfur 34. Chlorine, two isotopes, chlorine 35, 75%, and chlorine 37, roughly 25%. Bromine exists primarily in two isotopes, bromine 79, roughly 50%, and bromine 81, again, roughly at 50%. So we have a 50-50 distribution between bromine 79 and bromine 81. In chlorine, we have a 75 to 25 ratio. Iodine consists primarily of iodine 127. Primarily, that's the only isotope that's found. Are there other isotopes of iodine? Yes. Are they found to any significant amounts? No. Therefore, we call iodine 127 the most common, that's the weight of iodine is 127. So we can identify certain isotopes, excuse me, we can identify certain halogens by the mass spectrum. Chlorine will have an M peak and an N+2 peak. The ratio of the heights, this is 25, that's 75, basically a 3-to-1 ratio. Bromine will have two peaks in the parent molecular ion, but they are generally of equal intensities. Iodine will have a large gap and a peak at 127. So if you see something at 127, you've got iodine, there is no doubt. Then nitrogen will have an odd number parent molecular ion peak. So let's take a look at some spectra to give you an idea of what it looks like. So here we have the mass spectra of chloropropane. In the parent molecular ion range, 78, 3 carbons, chlorine, 7 hydrogens, comes to 78. We see 2 peaks, the M plus and the M+2 at 80. The M plus at 78 comes from the chlorine 35 isotope. The peak at 80 comes to the peak due to the isotope of chlorine 37. Basically, the heights of these things is a 3-to-1 ratio. Here we have the mass spectrum of bromine. This is 1-bromopropane. We can see down here in the parent molecular ion region, 122, C3, H7Br comes to 122 when the isotope of bromine we're looking at is bromine 79. But we have another peak that is 2 mass units higher. If this is 122, this is 124. From C3H7, bromine 81. So the difference of two mass units and the equal heights of these peaks down in the parent molecular ion region scream out, got bromine present. This is the mass spectrum of methyl iodide. I apologize for the fuzziness of this. I can't get a good spectra of it. We can see a huge peak at 127. This peak at 127 screams out, I've got iodine present. So 156 is 127 plus 15. What are we getting at here? Sorry, 127. 7, 5, 7, 4, 7, 5 is 12. 42. What am I missing? 15 plus 127. 12, 142. 56, so there's another. This is ethyl iodide. I apologize. That's ethyl iodide. It's not methyl iodide. I apologize. So this is ethyl iodide. So the difference between 127, which is the iodine, and 156, which is the parent compound, 156 minus 127 is 29, an ethyl group. So again, knowing what may be present in the compound, by the iodine, if you subtract out 127 from the parent compound, it should tell you what is left over after you lost the iodine. Since the difference was 29, 29 is most commonly the CH3CH2 group. Other kinds of organic compounds that are present that can fragment in unique ways. If it has a carbonyl, usually it can undergo what's called a McLafferty rearrangement, where we form the double bond here and form this resonance stabilized radical cation that's detected by your mass spec. Or you can undergo alpha cleavage. Here's your carbonyl. This carbon is bonded to something else. You can break either one of these carbon-carbon bonds. So it breaks and forms this radical fragment, or it breaks here and forms that radical fragment. Let's see if we can put our mass spectral knowledge to a test. What can we guess that the parent molecular ion and several other fragments that can be found in the spectrum of that molecule? Okay, well, I don't know if the colors are good enough for you to see. That is an oxygen. The red is an oxygen, the whites are hydrogen. Everything else, every black sphere is a carbon. So we have carbon, 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 carbon. So we've got a substituted 5-carbon compound. 1, 2, 3, 4, 5. This carbon 4 has the OH, and it has a CH3 there. So A, B, C, D, E, F. D, E, F. D is 2 hydrogens attached to this carbon E, attached to that carbon B. So H, D is attached to B and E. E has 2 hydrogens attached to D and F. 2 hydrogens here, and then F, this terminal carbon, 3 hydrogens. So what kind of functional group do we have? Well, we have an OH. What's one of the things that we can expect to see in a mass spec for a compound that has an OH group? When it fragments, we can expect to see dehydration, loss of water, loss of 18. So we might expect H2O loss, peak of 18. What's one of the other things that we can do looking at this compound? The other kind of fragmentation that alcohols can undergo is that the bond here can break or the bond there can break. Well, if we kick out that what I've circled, this is a CH3, which is a mass loss of 15. Or if we break the bond here between B and C, we can see a mass loss of 1, let me see, we can see a loss of 15. Or we can see mass loss there because D is also alpha to B. So we can see the mass loss of C123, C3, 1, 2, 3, 4, 5, 6, 7, C3H7. This is 36, plus 7 is 43. So we might see loss of 18, loss of 15, or loss of 43. Well, we start out with C, 1, 2, 3, 4, 5, 6, C6, O1, H, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C6H14O1. So we have C6H14O1. So C6H14O1 should come as 12 times 6 is 72, plus 16 for oxygen, plus 14. 16 and 14 is 30, 30 plus 72 is 102. So we should see a peak at 102. If we lose 18 for the loss of water, 102 minus 18, 9, so we might see something at 82. And loss of 15 from 102 minus 15 gives, let me see, 80, 87. So we might see something at 82 and 87, or the loss of the C3H7, which is 43, 102 minus 43, 59. So we might see something 87, 82, 59, and other consecutive losses of other things. Let's see. 87, 82, 59. And if this C3H7 breaks up, we might see even a 29. So the molecule is 2-methylpentanol. It produces fragments resulting from dehydration, so the loss of 18, and alpha cleavage. So we might see peaks at 102 for the molecular ion, 87, 4, and 59. So here's 102. We lose water, 18 from 102, 84. This is loss of water. If it breaks and loses an alpha cleavage of one of the methyl groups, you get down to 87. Or if this thing fragments internally, we get to see this fragment right here. We can see this kind of alpha cleavage and gets us to 59. So we can have all these three peaks identified just basically by knowing the simple rules for bond fragmentation and how the different kinds of functional groups fall apart. Real quick, I'll end this because the video is going a little bit long. Most biochemical analysis, when you're looking at amino acids, polypeptides, and proteins, usually use what are known as soft ionization methods, because the molecules themselves are not volatile, meaning that they're too large, they're too big, they're too heavy for them to go into the gas phase. Therefore, we have to introduce the sample in different ways such that it can be ionized, and then the fragmentations can be studied. One of the ways that this can be done is what's called electrospray ionization. Usually, the sample is injected but not volatilized, not heated until it goes into the gas phase, because it won't go into the gas phase because it's too big. It'll caramelize like sugar does. ESA, high voltage electricity, is passed through the solution sample. The sample can gain a proton from the solvent, which evaporates quickly. It forms a charged species. Since that charged species is of higher energy, it fragments, and we get our fragmentation pattern. So these compounds are not volatile, so we can't use those in the gas phase. This is a solution phase kind of analysis. It still gives us mass fragmentation patterns, but the fragmentation pattern is not caused by being blasted by a stream of electrons. Or there is called, and this is the lion's share of complex organic molecules, proteins, enzymes, RNA, DNA. It's what's called matrix-assisted laser desorption ionization, or MALDI. The sample that you're looking to analyze is inserted into a matrix of something, like glycerol, 1,2,3-pentane-triol. A matrix gel solution is on the tip of a probe. Your sample is introduced into that matrix gel solution on the tip of the probe. The probe is then inserted into a laser, into the laser path. The sample is exposed to laser light. Energy is transferred from the matrix to the sample itself. Then the sample fragments. So here in these processes, you're looking at causing the fragmentation indirectly. Something else happens first, then the molecule fragments. With EI kind of ionization, the molecule is blasted directly. These other methods involve something else happening first, and then that something else causes the compound to fragment. We'll end it here. Again, this is your video for Martin Luther King Day, January 18th, 2001. Hopefully this makes some sense. There are links to other videos that I've posted that cover mass spec If this particular way that I've described it is not really helpful, there are links to videos posted on the class page that may come at it from a different point of view that may be more helpful in getting you to understand the process. See you guys on Wednesday, January 20th. Have a good weekend.